Okay, class. So we're going to finish up the last lesson before the end of the semester, and you should have read all the way to the end of 6.3 so that you would see the geometric random variables. And hopefully you saw that they are very, very similar to binomial, and the way we describe them is very similar to binomial. Okay, so the basics. Each trial has two outcomes, right? And we count those outcomes as either success or failure. And it doesn't matter how many actual outcomes there are to the trial, even if it's like rolling a die, we're still only going to count it as either a success or failure. We get what we want or we don't. Okay, so that's like binomial. And each trial is independent. They have no effect on each other. Okay, so it has to be an independent thing that we're looking at for these geometric random variables, just like the binomials. And you have the same probability every single time. Okay, the big difference is that we're no longer counting the number of successes. Okay, we're not trying to figure out like how many kids out of 5 will have type O blood, okay, with a 25% probability. Now for geometric, we're actually looking for something very specific, and it's basically the number of trials we need to get a success. Okay, and so because we don't know how many trials we'll have to go through to get a success, the number of trials can no longer be predetermined. Remember, for binomial, that was a rule. You had to determine the number of trials ahead of time. Okay, if we're talking about a family of 5 children, it was 5 trials. If we're going to roll a die 10 times, then the number of trials was 10. But it had to be done ahead of time. Okay, so now we're basically counting the number of trials in order to get a success. So we're going to count it as basically fail, 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 success until we get, what we want. Okay, so with binomial, the acronym that we had for describing it was BINS, B-I-N-S, remember? Binary Independent Number of Trials and Success. Okay, so geometric is very close to it. Instead of BINS, it's BITS, because again, the number of trials is no longer predetermined. But B still stands for the same thing. B is still binary. Okay, I is still independent, which means that each trial does not affect the next one. Okay, and that sort of goes in with that probability of success not changing, right? If something is independent and has no effect on the next trial, then that's because the probability of success doesn't change. Okay, and just to make sure we remember that, I'm going to type that in so you can get it in your notes, that the success probability stays the same. The T, in this case for trials, is, again, to count the number of trials until you achieve a success. And only one specific success. We're not trying to count more than one, like with binomial, the chances of getting 3 out of 5 successes. We're not counting that anymore. We only want one success to happen, and we have to sort of count up how many times we're going to fail before we can succeed. Okay, so again, for the successes, that means that the probability stays the same. Okay, so that's the one major difference between binomial and geometric, is that we're not counting more than ever one success. And it makes the formula a lot easier, because when we did binomial, we had to have that NCR in the front, right? That combination of, well, how many different ways can I get 3 out of 5 successes? I could get the first 3, the last 3. That's why we have that first part of the formula. Well, think about it now. All we're counting is fail, 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 fail until we get to a success. Okay, so that means we're only looking at the last part of that binomial formula, and we're never going to have more than one success. So it really makes the formula a lot easier to do by hand, although we will talk about doing it in the calculator. So yes, this is very, very similar to binomial. If you have an open response question that deals with a geometric, this is what you will have to prove for it to be geometric: binary, independent, counting trials until you get a success, and that your probability stays the same. Okay, so just like with binomial, it is a random variable, and you are going to be doing a probability distribution. It is a table. The only difference is the table in this case could be infinite, right? Because we could count up till 1,000,000 failures until we get a success if we wanted to. I don't know about you, I don't want to make a table that big, but it is the same concept as far as doing the distribution. And because your number of successes are whole numbers, or your number of failures are whole numbers, right? You don't have to worry about doing all the little in-between things. You know what your outcomes are going to be. Okay, so we're counting the number of trials until we get our first success. Okay, so we still have P, little p being our probability of success, right? We just don't have N anymore at all because there is no set number of trials. What we have is basically, again, a choice of how many failures do you want to go through until you get a success. Okay, so normally we use X for binomial, and we use Y for geometric when we're doing our big probability statements, right? Like before we were doing probability of A, and that would be like boys who had pierced ears. For binomial, generally you use large X, capital X. For geometric, you normally use capital Y. Okay, so the actual formula, and it's really short, really easy to get any kind of a distribution for it, is this. Okay, so 1 minus P, we remember, is the probability of failure, right? And however many counts we're talking about, we want 1 minus that to be the number of failures, because obviously our last trial is going to be our success, whatever we count it as. Okay, so I'll give you another minute to make sure you've got all this down. And then we'll actually do some practice ones. Just in case you missed anything. Now, in case you're getting a little confused as far as the way it's explained, again, you already know what a probability distribution is. We've been doing it for several chapters now. That's just the little table that talks about all the different outcomes and the probability of them happening. Okay, so basically all this is saying is that, like binomial and like normal probabilities, it's just a distribution. You can write it as a table. Okay, so don't let that stress you as far as the definitions or the explanations for it. It's just a fancy way of saying that we can write it as a table. Okay, so we have the formula. Let's go ahead and start applying it, and we'll do the hard way, long way with the formula first, and then we'll talk about how to put it in the calculator. It's in there in the distribution menu, just like with your binomial. You just only have to worry about 2 different variables now. There is no n. All right, so let's do a practice. Okay, so an entire deck of cards, right? No jokers. Just in case you're not familiar, for those of you who don't play with cards, if you have an entire deck of cards with no jokers, that's 52 cards, okay? So we have 52 possible outcomes, right? And we're going to somehow separate that into successes and failures, okay? So what's considered a success in this example is flipping over a face card. Okay, so again, those not familiar with a deck of cards, okay, there's jacks, queens, and kings that count as face cards, and there are 4 of each: diamond, heart, spades, and clubs. Okay, so you have 12 out of 52 is your probability of success, right? 12 out of 52. And you can put this in the calculator and you can raise that to an exponent. It's fine. You have the fraction capability on both calculators. And it's the same thing. It's the alpha y equals, remember, to get your fractions. We can, however, reduce this at least to make the numbers, it's not going to matter in the end, but to make the numbers a little smaller that you put in. 12 out of 52 is 3 out of 13. So you can reduce it at least. So that is my chance of success. So that means my chances of failure, since that's what we have to put in the calculator as well. 1 minus this, right, would be 40 out of 52 or 10 out of 13. Okay, and that's really all we need is the probability of success and failure. And then we have to decide how many trials do I want to go through before I get a failure. As far as when I'm checking this, as far as the probability, how many times do I want to say that it's possible to fail before I get a success? Okay, so for the example question, what's the probability that you'll have to flip over 5 cards before you get a face card? Now keep in mind, that means that you'll get a face card on your 6th card, not your 5th. It means you have to fail 5 times and then you get a success. Okay, so how you would write that is the probability of y equals 6. Okay, this is a singular probability. Okay, we're not doing a less than or equal to until we start talking about doing this in the calculator. We're not doing a greater than or equal to, definitely, until we get the calculator. Okay, so we can do a singular binomial by hand. So y equals 6. That means I'm going to succeed on my 6th trial. Okay, so the setup for that would look like this. I have my probability of failure, 10 out of 13, 5 of them, times 1 success, and it would be 0.062. So about 6.2% chance that I'll have to flip over 5 cards that won't be face cards, and then I'll get a face card. Now, in your calculator, again, in that distributions menu, it's right near, I think, the binomial one. It's either before or right after it. Notice there are only 2 variables we're putting in, right? There's no more n anymore, no number of trials. All it's going to ask you for is your probability of success and which trial do you want to succeed on, okay? So you'll put that in, you'd put this in the calculator as 3 out of 13, comma 6, right? You want to succeed on your 6th trial. Okay, and it should come out to pretty close to 0.062, depending on rounding. Okay, so that's a geometric PDF. And again, that is for a singular, just like when we were doing binomial PDF. Now, here's the difference, okay? What's the probability that you will have to flip over at most 6 cards? Okay, at most meaning 6 or less, I hope you said. We could do this just like we did with the binomial PDF. I could make a distribution table, so could you, from this, and you would have to find out the probability of having 0 failures and 1 success, 1 failure, 1 success, all the way up to 5 failures and 1 success. And you could actually fill out the table and then add it all up, and you would be able to get the probability of at most, less than or equal to 6, okay? In your calculator, again, under the distribution menu, go to the geometric CDF. Okay, so CDF does the same thing here that it did in binomial. It counts from left to right, okay, and it is cumulative, and it stops on the number that you put in, okay? So probability of y is less than or equal to 6, so I'll be putting in 3 out of 13, comma 6, with the CDF, is 7.79, so about a 79% chance that 6 is the most amount of cards you'll have to flip over till you get a success. Okay, these are not difficult. In fact, these are a little bit easier than binomial because there's 1 less variable to deal with. All right, same thing with binomial. What if I wanted to leave off the equal to, right? We talked about this yesterday. If I specifically said the probability that y is strictly less than 6, right? This is the same exact thing as binomial. That is the same thing because of the way the outcomes work. as the probability of y being, let's pull up my math symbols, not that. There we go. There we go. Less than or equal to the next number down. Because from the lesson yesterday, if I say strictly less than 6, then I'm counting from 0 all the way up to 5, right? And I'm just not including 6. And you would put it in the same way. I don't have my calculator on me right now, so obviously it's going to be less than 79% because we're leaving off some other probability. Okay, so if we're doing the greater thans, right? If we're doing probability that y is strictly greater than 6, remember that is counting 7 and up, right? And 7 up to infinity as far as the geometric is concerned, right? So we are not counting 6 in our probability, so it would be 1 minus, we need to leave off 6 and below, the probability of y being less than or equal to 6. Okay, same rule as yesterday. If I want greater than 6, then I have to take off 6 and below from my 1 because that is what my distribution adds up to. Okay, what if I want to do a greater than or equal to? Again, same exact rule as yesterday. Okay, if I want to do a greater than or equal to 6, that means 6 and up is what I am counting, right? So that means I have to leave off everything below 6. So that means I can't type 6, right, into the geometric CDF because it will count 6. So I would have to do 1 minus the probability, or 1 minus the probability of y being less than or equal to 5. Okay, so as a geometric CDF, you would put in, again, your probability of success is 3 out of 13, and the number of successes we want to count all the way up to would be 5 for that one. Okay, and then this would be 1 minus Geomet CDF, and I'm going to run out of room. And the Geomet CDF on this one, again, 3 out of 13. Make this a little bit smaller so I can get it to fit. Okay. And what am I leaving off? I'm leaving off everything below 6. So 3 out of 13, comma 6. Okay, and that would give me everything above 6 all the way up to infinity. All right, and then this one, 1 minus Geomet CDF, and again, 3 out of 13, and then since I'm counting all the way up to 5, and including 5 that I'm taking off, it would go in as 3 out of 13, comma 5. Okay, so again, very, very similar. And in fact, this is identical to the rules for binomial, but very, very similar in that the only real difference is, again, the number of trials is not chosen. Okay, all we can try is when I want to get the success. Okay, so that's pretty much it as far as that. The only thing, we already did this, the only thing that's different is how we find the mean of a geometric. Now, the mean of a binomial, remember, is your number of trials times your probability, NP, right? And then the standard deviation was the square root of n times p times 1 minus p, okay? Well, remember, we don't have n anymore, okay? We don't have a set number of trials. So the expected value of a geometric is just 1 divided by the probability. Okay, so in our case, our mean would be 1 divided by 3 over 13. which is again why I wanted to leave it as a fraction and not put it in a decimal. Well, 1 divided by 3 over 13, if you group it and put it in your calculator the way you're supposed to, should give you 13 divided by 3, which is about 4.3. So our average, as far as the average amount of cards we would have to turn over till we got a face card, and you can, play with this over Christmas if you want. Take a deck of cards without jokers and shuffle it up and start flipping them over one at a time and write down how many cards it takes you to actually get to a face card. And keep in mind that when we're talking about the mean and the expected value, we're talking about the law of large numbers, right? This happens over a long period of time. What will happen is that, and by the way, that is 4.3 repeating, I know. What will happen basically is that your average, if you keep adding, all the different times, do all the different simulations for it, you're going to get an average of about 4.3 cards. And obviously I know you can't turn over 4.3 cards because we're talking about a long run here. But that would be the average if, you add all your trials together. Okay, so that is it. It's a very short lesson. I only want you to do these 4 problems for geometric, and I will be sending out tomorrow the list that you have to turn in Friday for Chapter 6. All right, behave yourselves.